Good evening, everyone. So, today we are in the practice assignment session for the course contents covered in week 5. All of you, please get ready with a pen and paper so that we can solve problems. Let us begin. The continuous time system with input x of t and output y of t related by y of t equal to tan of x of t is dash. So we are seeing about the causality and stability of systems. Our system equation is y of t is equal to tan of x of t. So what kind of a system is this? So write about the try to write the condition for causality and stability of systems and see where this system fits in. Okay, so let us see when the system is said to be a causal system. A system is said to be causal if its output depends upon present and past inputs and does not depend upon the future input. Causal systems are practically realizable systems. So, when we have a system whose output depends only upon the present and past inputs and not on the future input, those systems are called as causal systems. For example, y of n is the output of our function of our system, and say if the system has f, say f is some function, okay, so it depends upon x of n, x of n minus 1, x of n minus 2, etc. So these things, x of n minus 1, n minus 2 means it is present and past inputs. So this output y of n depends upon present and past inputs. So this system is a causal system. Another example is integration here. So y of t is 1 by c integral minus infinity to t x of tau d tau. So if we see the limits, It is from minus infinity to t. So it is from the past inputs up to the present input. So this system is also a causal system. When a system is called non-causal means the output depends upon future inputs. Then the system is non-causal. For example, if our y of n depends upon x of n plus 1, n plus 2, if it depends upon future inputs, then this system is a non-causal system. Same way, another example is y of t is equal to x of minus t. Then again this system is a non-causal system. The second thing is stability. When when is a system said to be a stable system? Only when the output is bounded for bounded input. So when your input is bounded, the output must also be bounded for a stable system. What is meant by that? So if for example y of n is equal to x of n. So if x of n is less than infinity, y of n is also going to be less than infinity. Another example is y of t is sine of x of t. So here if your input is bounded, if x of t is bounded, what is the limit for a sine function? It is just plus or minus 1, right? So if your input is bounded, y of t is also going to be bounded. So these two are examples of stable systems. For a bounded input, if the output is unbounded, then the system is said to be unstable. So when your output is unbounded, your system is unstable system. For example, y of n is n into x of n. So even if your input is bounded, okay, even if your input is bounded, if n tends to infinity, y of n may tend to infinity. Same for the case of y of t equal to t into x of t. So when your input is bounded, the output may become unbounded. So these systems are examples of unstable systems. So with these two definitions of causality and stability, let us see how to solve this problem. Y of t is tan of x of t. Okay. So y of t, like if you consider t, it is just tan of x of t, right? So the output depends only upon the present input, just the time t, just present input. So this system is a causal system. There is no dependence on future inputs. Okay, so the system is a pure causal system. If x of t if x of t is less than infinity, even if x of t is less than infinity, y of t may tend to infinity. That is, what is tan of 90? It goes to infinity, right? So even if the input x of t is bounded, y of t may tend to infinity. So this system is not a stable system. So the answer is causal but not stable. Okay. Moving on to the second question. The continuous time system with input x of t and output y of t is related by y of t is equal to 1 divided by x of tan of t. Now, what kind of a system is this? So, our system is y of t is equal to 1 divided by x of tan of t. Are you guys trying this? Okay. So, the answer is it is neither causal nor stable. Let us see how. For a particular t, tan of t can have a value larger than t. So, the output y of t may depend upon future input also. So, if we have a particular t, if you take tan of t, that value may be greater than t also, right? So, this output is now depending upon future inputs also. So, the system is a not causal system. And since tan of t is unbounded, y of t may also become unbounded. So, the system is not a stable system. So, the answer is neither causal nor stable. Okay, we are moving on to the next question. Which of these systems is linear but not time invariant? Okay, let us try to understand about linearity and time invariance. A linear system should obey law of additivity and law of homogeneity. So what is law of additivity? If I have x1 of t, if I am passing through a system and I am getting y1 of t, okay, and I have x2 of t, I am passing through a system, I am getting y2 of t, and then I am adding the outputs. So I am just adding the outputs from the systems, okay. Now if I give an input to the system x1 of t plus x2 of t, then my output should be y1 of t plus y2 of t. Basically, after the system, if you add the outputs, that should be same as adding the inputs and then giving to, and that output should be same as adding the inputs and giving it to the system. This is the law of additivity. What is law of homogeneity? If I have a system, the output is y of t and then I am scaling the output. Okay. Now this output k into y of t, this should be same as scaling the input and then giving it to the system. So just directly scaling the output and then scaling the input and giving it to the system, their outputs should be the same. This is law of homogeneity. So a linear system should obey law of additivity and law of homogeneity. Generally, there are some quick checks what you can do to say whether the system is linear. Okay. First is the output should be 0 for 0 input. If your input is 0, if x of t you are giving as 0, your output should also be 0. That is first check. Second check is there should not be any non-linear operator present in the system. If these two things are there itself, approximately you can tell that the system is a linear system. Here we have two examples. First, y of t is 3 into x of t. First, let us take 0 input. X of t is 0. What is our y of t? 0. And there is no non-linear operator in this. So this system is a linear system. Second example is y of t is equal to x of t plus 3. Even if your x of t is 0, even if you give 0 input, your output is not 0. Y of t will be equal to 3, right? So this system is a non-linear system. Here we have shown the property of homogeneity. So this equation y of t is equal to x of t plus 3. This does not follow law of homogeneity. So how I am checking it here? I am scaling output, okay, a into y of t. What this will become? A into x of t plus 3. So a into x of t plus 3a. This is not equal to scaling the input and giving it to the system. If you scale the input, it is a into x of t, right? If I give it to the system, I will get a into x of t plus 3. So this output and directly scaling the output, these two outputs do not match. So this system does not follow the law of homogeneity. Is this clear for everyone? Am I audible, guys? Okay. Next is time invariance. A system is said to be time invariant if the system's output is the same given the same input signal regardless of time. What does this statement mean? Any delay provided in the input must be reflected in the output for a time invariant system. So, I have input x of t. I am passing it through the system. I am getting y of t. Now I am delaying the output. So it is y of t minus some small t or some tau. Okay. This output should be equal to giving a delayed input to your system. So second, what I am doing, I am delaying the input. So x of capital T minus small t. Now I am giving it to the system. This output and this output, both these outputs should be the same. So any delay provided in the input must be reflected in the output. If you have such a system, then it is said to be a time invariant system. For example, for a time invariant system, I am having y of t is equal to sine of x of t. So this will follow this property, time invariance property. For a time variant system, I have an example, y of t is x of 2t. So, y of t minus tau, okay, is what? X of 2 2t minus tau. Correct? This is directly I am delaying the output. Second thing is, now I am delaying the input. So instead of x of t, I am giving as x of t minus tau. So I am giving a delayed input, so that will be 2 of t minus tau. And now, so this is the output for the second case. I am delaying the input and giving it to the system. This is directly I am delaying the output. If you see, these two are not the same. So this system is a time variant system. Now let us see what the given systems were. Okay. First step, y of t is 3 into x of t. We saw this example previously. It is a linear system directly, and it is also a time invariant system. That is, even if you directly delay the output, or if you delay the input and then give it, both of them are going to give you the same result. For example, if I am delaying the output directly, it is 3 into x of t minus tau. And then if I delay the input and give also, my output is going to be 3 into x of t minus tau. So they both will be same. For the second case, y of t is 1 by x of t. Basically, you have a non-linear operator, right? So directly the system is a non-linear system. And it is a time invariant system also. D option, we have x of t plus 3. We saw this example also. It is a non-linear system. What is our question? To find the system should be linear but not time invariant. So your options, so you will just have to check between A and C. If you check C, it is a linear system, but it is not time invariant. So if you directly delay y of t, I am going to get y of t minus tau, right? And then I am going to delay the input and then send. So I am going to send x of t minus tau into the system. So that I am going to get as x of 1 by t minus tau. So this and directly delaying the output, they both are not the same. So delaying the input and sending to the system and directly delaying the output, they are not the same. So this is a time variant system. The answer for our question is option C. It is linear but not time invariant. Is anybody having any doubts in this question? Okay. I'm moving on to the next question. Which of these systems is time invariant but not linear? It should be time invariant, but it should not be linear. So first, what you can do is elimination strategy you can follow. It is not linear is the question. So directly you can eliminate this. And then we are looking into time invariance. So with that, how do you shortlist your options? And then finally you try to see which system is time invariant but it is not linear. So the answer is B. Our question was time invariance and non-linear. So directly we eliminated A, C, D because the systems are linear. And if you see, only B is non-linear and it is also time invariant. How is it time invariant? If I directly delay the output y of t minus tau, it is going to be x of t minus tau plus 5. If I delay the input and then pass it through the system also, it gives you the same result. So it is time invariant. And how is it non-linear? If I take y1 of t which is x1 of t plus 5. y2 of t is x2 of t plus 5. If you add a into y1 of t plus b into y2 of t, I'm going to get something like this. So I'll get a into x1 of t plus 5a plus b into x2 of t plus 5b. Now, if I directly add and scale the input and then give it to the system, that is, if I give the input which is a into x1 of t plus b into x2 of t, if I give this to the system, my output will be only a into x1 of t plus b into x2 of t plus 5. So this 1 and 2 are not same. So the system is not a linear system. Basically, what we are trying to do by doing this is, we are checking both homogeneity property and additivity property, a into y1 of t plus b into y2 of t. So additivity property also we are checking, homogeneity property also we are checking. So if you see that 1 is not equal to 2, so the system is a non-linear system. So the answer is 4. Sorry, B. Okay. Moving on to the next question. Which of these systems is neither time invariant nor linear? So it should not be time invariant also, it should not be linear also. So again, this is clearly a linear system, so we can leave this. So now you have to check between A, C and D. The answer is option D, guys. So we are finding which of these systems is neither time invariant nor linear. So uh, even A and C are non-linear, but both are time invariant. So let us check option D. So for non-linear, we know how to check. So if I do A into y1 of t plus B into y2 of t, this, and if I give as input A into x1 of t plus B into x2 of t into the system, what I am getting is second. Okay, so 1 is not equal to 2. So directly the system is not a linear system. How do we check time invariance? First we delay by y of t. So y of t minus tau, if I do, it is x of 2 minus t minus tau plus 2. If I delay x of t and then pass it through the system, if I delay x of t, it will be x of t minus tau. That I am passing it through the system. So what will be y of t? X of 2 minus of t minus tau plus 2. So if you see 1 and 2 are not the same. Here we have 2 minus t minus tau. Here we have 2 minus t plus tau. So this shows that the system is time variant. So it is not linear and it is time variant. So the answer is option D. We are moving to the next question. Consider a series RLC circuit in which the voltage output is measured across the capacitor. So the voltage output is measured across the capacitor. What is the ratio of the Fourier transforms of the voltage output and input, and what kind of a filter is it? So try to imagine a RLC circuit, write down its equations, and the voltage output is measured across the capacitor. Now, what kind of a filter will it look like? Okay, let us see how to do this. We are considering a series RLC circuit, okay, and our input voltage is Vi of t. Now, if I take a capacitor, the charge in a capacitor is C into Vc. So, it is the product of capacitance into voltage across the capacitor. Now, if I have to write the equation for current, I is rate of change of charge, right? So, I is equal to dq by dt. Now, dq by dt, I can write it as C into dv by dt. So, the equation for a capacitor is I is equal to C into dv by dt. If I have to write it in its Fourier transform, so taking Fourier transform, I of j omega is C into, since there is differentiation here, you have j omega. So I of j omega is equal to C into j omega into Vc of j omega. So this is the equation for a capacitor. For an inductor, we know that the voltage across the inductor VL of t is L into di by dt. Now, writing it in its Fourier transform way, VL of j omega is L into j omega into I of j omega. So, when I have a series circuit like this, the current that passes through the circuit is going to be the same. That is why for I don't have any notation. But voltage across different components are different. So, I have for capacitance I have written Vc of j omega, for inductance I have written VL of j omega. So, these are the equations for a capacitor and inductor. Now, we have to use this into our equation. So, we have a series RLC circuit, right? So, Vi of t, whatever is our input voltage, is I into R, voltage across resistance, plus voltage across inductance, plus voltage across capacitance. Now, taking Fourier transform of this expression, Vi of j omega is I of j omega into R plus, for in inductance we saw previously, right, j omega L into I of j omega. For capacitance, I am keeping it as V naught of j omega. Why? We are seeing the voltage output across the capacitor. So, since we are seeing the voltage output across capacitor, Vc of t, I am keeping it as V naught of j omega. Now, what we are doing here is, we are writing I of j omega in terms of this V naught of j omega. So, how will it be? What we saw here, for capacitance, I of j omega is equal to j omega c into Vc of j omega. For inductance, if you have to write I of j omega, it is VL of j omega by j omega L. So, we have to use these two things here, and then Vi of j omega, we will, in terms of V naught of j omega, we can write. What are we asked to find? The ratio of Fourier transform of voltage output and input. So, V naught of j omega by Vi of j omega we have to find. So, that is 1 divided by j omega RC, and j square it is minus 1. So, minus omega square LC plus 1. Now, we have to find what kind of a filter is this. How are we finding that? I am finding the magnitude of the ratio of output to input voltages. So, it is 1 by j omega c divided by R plus j omega L plus 1 by j omega c. Now, if omega is large, if omega tends to infinity, for example, what does this numerator become? 0. correct? So if for large omega, the magnitude is becoming very small. What does this mean? For large frequencies, the magnitude or response of the filter is becoming very small. It is actually tending to 0. So, it is rejecting large frequencies. So, it is just allowing lesser frequencies. So, it's basically a low pass filter. So, in a series RLC circuit, if I measure the output voltage across capacitor, now it is a low pass filter with this kind of a output to input voltage ratio. Now let us see a similar example. Now it is the same series RLC circuit, but voltage is measured across the inductor. Now what is the ratio of Fourier transforms of voltage output and input, and what kind of a filter is it? So you guys try to draw a series RLC circuit and keep V naught as voltage across the inductor now. And can you tell what kind of a filter is it? So now the voltage output is measured across inductor. So this is V naught of j omega for us. So the input voltage is sum of voltages across resistance, inductance and capacitance. So Vi of t is I into R for voltage across resistance and VL of t for inductance, Vc of t for capacitance. And V naught of j omega is with respect to inductor for now. So we are taking Fourier transform. So Vi of j omega is I of j omega into R plus V naught of j omega plus with respect to Vc of t, Vc of j omega means I of j omega by j omega c. Now we have to write I of j omega in terms of V naught of j omega. That is with respect to inductance, how our I of j omega we can write. I of j omega we can write as V naught of j omega by j omega L. So plus V naught of j omega, same way I of j omega in terms of voltage across inductor, we should be able to write it as V naught of j omega by j omega L. Now same way we are finding V naught of j omega by Vi of j omega. So you rearrange this expression and then we are going to get this answer. Now if I find the magnitude, if I put omega as a very small value, okay, if omega tending to 0, my magnitude is going to tend to 0. What does this mean? My magnitude response is almost 0 for lesser frequencies, lesser range of frequencies. So this allows only higher range of frequencies. So it is basically a high pass filter. So the basic idea is what? We have a series RLC circuit. The input voltage is equal to sum of the voltages across the resistance, inductance and capacitance. Then we are writing their Fourier transform versions. And we see across what component we are measuring the output voltage. That we will keep it as V naught of j omega. Then we will write everything in terms of Vi of j omega and V naught of j omega, and then you can simplify and get the answer. Okay. So it's the same question, but now we are measuring the voltage output across resistance. Okay. So it is the same logic, but now we are measuring the voltage output across resistance. So this will become V naught of j omega. Across resistors will become in V naught of j omega. Then for inductance and capacitance, we will write the equation. Now we have to write I of j omega in terms of the voltage across resistance. So V is equal to IR, right? So I will be equal to V by R. So V naught of j omega plus j omega L into V naught of j omega by R. Same way here also V naught of j omega by j omega RC. So it's the same thing, but just we are rearranging it. So now again we are going to find V naught divided by Vi. We are coming to this answer. Now what I am doing here, I am dividing the entire numerator and denominator by j omega c. So numerator will become R, denominator will become j omega L plus R plus 1 by j omega c. Now in this, if you see, what will happen if you have so even if you take smaller values of omega, if omega is tending to 0, for example, then also this filter is not going to allow signal to pass through. If omega is higher range, if omega tends to infinity also, this filter is not going to allow frequencies to pass. So basically this is a band pass filter. So the option is B. In a similar lines, we have few more examples also. Now see, we just have a RC circuit here. what is the ratio of output voltage to input voltage and what kind of a filter is this. We just have to follow same kind of setup. So if I have an RC setup, I just have to follow the same kind of expressions, okay. So V naught of j omega is that across the resistor, okay. So it is Vi into R divided by R plus 1 by j omega c. So here the capacitance and resistors are in series. So we are finding the voltage across the resistance. It will be the ratio of R divided by R plus 1 by j omega c into Vn. Now V naught by Vi, we will get the expression. And if I consider low frequencies, we are seeing that if omega is approximately tending to 0, the magnitude is tending to 0. And if I take omega as 1 by RC, then the magnitude is 1 by root 2. For higher omega, when omega tends to infinity, if I apply L'Hopital rule, I am getting the value as 1. So basically, if I see the response of this filter, it is almost 0 for lower frequencies and it is just becoming 1 for higher frequencies. So this is a high pass filter. So the idea is the same for all these set of equations. So we are trying to find the ratio of output to input voltage. We are seeing the magnitude response and we decide what kind of a filter is this. So let us see few more examples quickly. Same way here we are trying to find across a capacitor and a series combination of a capacitance and a inductance. So for this also, our V naught across this inductance will be Vn into j omega L divided by j omega L plus 1 by j omega C. So the equivalent value we are writing here. So Vn into j omega L by j omega L plus 1 by j omega C. Same way we are finding the ratio of V naught by Vn. We are getting this expression. And if I see for lower values what happens, it is 0. For omega tending to 1 by root LC, this expression, if I write omega tending to 1 by root LC, this expression is tending to infinity. And when omega tends to infinity, by applying the L'Hopital rule, I am getting the value 1. So again what I am seeing is, it is almost the magnitude response is, it is 1 only for higher frequencies. So this is again a high pass filter. Now, how can we write the equation when you have a combination like this? So we have R and then LC like this. So the output, so V naught of T is now the voltage across the series combination of L and C. So how our expression will be Vn into j omega L plus 1 by j omega C divided by total resistance. So R plus j omega L plus 1 by j omega C. So same way we are writing an expression. Here what we are able to see is at omega tends to 0, it is 1. And For omega tends to infinity also it is 1. So it is allowing lower frequencies also, it is allowing higher frequencies also. But at this specific point of 1 by root LC, it is actually becoming 0. So this is basically a notch filter or a band stop filter. At a particular set of frequencies it's becoming 0. So it's a band stop filter. Now, instead of this series combination of C and del, what if I had a parallel combination? Now, how will you write the equivalent resistance value? If I have two things in parallel, it will be R1 into R2 divided by R1 plus R2, right? Same thing will come here also. So, equivalent impedance is basically we have the inductance and capacitance in parallel. So R1 into R2 j omega L into 1 by j omega C divided by R1 plus R2, basically Z1 plus Z2. So j omega L plus 1 by j omega C. So the equivalent impedance is j omega L divided by 1 minus omega square into LC. Now the output is across this combination, parallel combination of capacitance and inductance. So V naught is Vn into Z equivalent plus R, divided by R plus Z equivalent. So the impedance across, like what we are going to measure the voltage, divided by total impedance. This is the logic. So Z equivalent divided by R plus Z equivalent. Again, now we will be getting an expression for V naught divided by Vn, and then we will be seeing the magnitude response. Here, for omega tends to 0 and omega tends to infinity, both the magnitude response is becoming 0. So this basically allows only a band of frequencies to pass through. So this is a band pass filter. So is anybody having any doubts? If nobody is having any doubts, we can end today's session. Thank you all.